Find the volume of the solid bounded below by the plane z equals 3 and above by the sphere x squared plus y squared plus z squared equals 4 squared. The volume of the 3D region R is given by the triple integral shown here, where when using spherical coordinates, dv equals rho squared sine phi d rho d phi d theta, and when using cylindrical coordinates, dv equals r dz dr d theta. We'll show the setup of the triple integral using both cylindrical and spherical coordinates, and then we'll evaluate the easier triple integral. Let's first look at this in 3 dimensions. Our goal is to find the volume of the solid above the plane and below the sphere, which should be this solid here. To help us determine the limits of integration, we will slice this vertically and also project the intersection of the plane and the sphere onto the xy plane. Before we do this though, let's review spherical coordinates. In spherical coordinates, rho is the distance between the point and the origin. Theta is the angle counterclockwise from the pole or positive x-axis in the xy plane, and phi is the angle between the positive z-axis and the point. Going back to our work, looking at the vertical slice, we know this length is 4, the radius of the sphere. We know this length here in the right triangle is 3, because this horizontal line is determined by the plane z equals 3. This should be the angle phi. Now looking at the triple integral, the first step is to find the limits of integration for rho, which again is a distance from the origin, which again is a distance from the origin to any point in the solid. We'll notice how the lower limit of rho will be determined by this horizontal line where z equals 3. So we know z equals 3 along this horizontal line. We also know z is equal to rho cosine phi. So if we substitute 3 for z, we have 3 equals rho cosine phi. Dividing both sides by cosine phi, we know rho is equal to 3 divided by cosine phi, along this horizontal line where z equals 3, which does give us the lower limit of integration for rho. So here we have 3 divided by cosine phi. The upper limit of integration for rho would be the distance from the origin to this piece of the sphere, and because the sphere has radius 4, the upper limit of integration for rho is 4. Now let's determine the limits of integration for phi, which should be this angle here. Using this right triangle, notice how cosine phi is equal to 3/4. So if cosine phi is equal to 3/4, if we take the inverse cosine or arc cosine on both sides of the equation, we have phi is equal to inverse cosine of 3/4, which means the limits of integration for phi are from 0 to inverse cosine 3/4. And then for theta, if we were to project this intersection onto the xy plane, we get this circle. We can determine the equation of this circle 2 ways. Using the equation of the sphere, we can substitute 3 for z, which gives us x squared plus y squared plus 3 squared is equal to 16. Simplifying, we get x squared plus y squared equals 16 minus 9 is 7. R squared is equal to 7, meaning r is equal to the square root of 7. We could also determine the radius of the circle by looking at this right triangle again. Using the Pythagorean theorem, 4 squared minus 3 squared is equal to 7, and therefore this length has to be square root of 7, the radius of this circle. Either way, theta is going to be all the way around the circle from 0 to 2 pi radians. So this is the setup using spherical coordinates, which because this solid involves a circle, seems like it would be easier. But let's also set this up using cylindrical coordinates. For a quick review, using cylindrical coordinates, r is the directed distance from the origin in the xy plane, theta is the angle counterclockwise from the polar axis or positive x-axis in the xy plane, and z is the directed distance up or down from r comma theta to the point, which are all pictured here. Looking at the setup, the first step is to determine the limits of integration for z. The lower limit of integration is determined by the plane where z equals 3. The upper limit of integration for z is going to be determined by the sphere, which we know has an equation x squared plus y squared plus z squared equals 16. If we solve this for z, we have z squared equals 16 minus x squared minus y squared. And therefore z is equal to the square root of 16 minus x squared minus y squared. But let's write that as minus the quantity x squared plus y squared. We need to express z in terms of r and theta, and x squared plus y squared equals r squared. And therefore z is equal to the square root of the quantity 16 minus r squared, which gives us the upper limit of integration for z. Next are the limits of integration for r, looking at the projection of the intersection of the plane and sphere onto the xy plane. We know the radius of the circle is square root 7, and therefore the limits of integration for r are from 0 to square root 7. And then for theta, the limits of integration are from 0 to 2 pi all the way around the circle. So it's going to be easier to evaluate this triple integral using cylindrical coordinates rather than spherical coordinates. So let's begin evaluating this triple integral. We begin by integrating r with respect to z. The antiderivative is r times z. When determining big F of b minus big F of a, we substitute the limits of integration for z, not r. Let's do this on the next slide. We will have r times the square root of the quantity 16 minus r squared minus 3. Let's go ahead and simplify this. Next, we'll distribute the r. Let's write this as r times the quantity 16 minus r squared to the power of 1/2 minus 3r. And now we integrate with respect to r. When integrating here, though, we need to perform u substitution, where u is equal to 16 minus r squared. Differential u is equal to negative 2r dr. Dividing both sides by negative 2, we have negative 1/2 du equals r dr. Which means when integrating here, we'll have an extra factor of negative 1/2. In terms of u, we'd have negative 1/2 du times u to the 1/2. So we'd have negative 1/2 times u to the 3/2 divided by 3/2, which is the same as multiplying by 2/3. Negative 1/2 times 2/3 is equal to negative 1/3. And then u to the 3/2 is really the quantity 16 minus r squared to the 3/2. And then we have minus 3 times r squared divided by 2, or 3/2 r squared. Now we need to find big F of b minus big F of a. When r is equal to the square root of 7, the square of the square root of 7 is 7. 16 minus 7 is 9, so we have negative 1/3 times 9 to the 3/2 minus 3/2 times, again, the square of the square root of 7 is 7, so we have 3/2 times 7. And then when r is 0, we'll have negative 1/3 times 16 to the 3/2 minus, this would be 0. Let's continue on the next slide. 9 to the 3/2 is equal to 27. 16 to the 3/2 is equal to 64. This simplifies to negative 9 minus 21/2, and we have minus. This simplifies to negative 64/3. And all of this simplifies to 11/6. So we have the integral from 0 to 2 pi, 11/6 d theta. And now we integrate with respect to theta. The antiderivative is 11/6 theta. Then we find big F of b minus big F of a one more time, which is 11/6 times 2 pi minus 0, which equals 11/6 times 2 pi. Simplifying, the exact volume is 11/3 pi, and this would be cubic units because it is volume. So now we know the volume bounded above by the sphere and below by the red plane is exactly 11/3 pi cubic units. I hope you found this helpful.